Of all the sea monsters that have captured human imagination, none have been as enduring or as terrifying as the Kraken. This legendary creature has long been a source of fascination, haunting the tales of sailors and writers alike. The word Kraken originates from Old Norse, with its earliest depictions dating back to the Icelandic sagas. These ancient stories portrayed the Kraken as a gigantic, octopus-like creature that could rise from the ocean's depths, wrapping its massive tentacles around entire ships and dragging them to a watery grave. Over time, the legend of the Kraken grew, fueled by sightings of strange sea creatures and the mysterious disappearance of ships. In 18th century Europe, tales of the Kraken reached their height, cementing its place in maritime lore. Naturalists of the time, lacking a clear understanding of marine biology, were willing to entertain the idea that such a creature could exist. The Kraken's size was described in increasingly dramatic terms, with some reports claiming it spanned miles in diameter. Artwork from the period showed the creature with numerous tentacles, thrashing waves as it pulled down ships and men into the dark sea. The mythical accounts were so compelling that even some early scientists began to speculate that this beast could be a reality, attributing unexplained shipwrecks and maritime disappearances to the monstrous Kraken. The renowned Swedish naturalist Carolus Linnaeus, known for his groundbreaking work in taxonomy, even included the Kraken in the first edition of his Systema Naturae in 1735. He listed the creature as a cephalopod mollusk, giving it the scientific name Microcosmus marinus *. Though he later removed it from subsequent editions, the fact that Linnaeus initially recognized the Kraken speaks to the widespread belief in the creature's existence during this period. This willingness to accept the Kraken as more than mere legend was not entirely unfounded. Stories and sketches of bizarre sea creatures provided tantalizing hints that the ocean might indeed harbor giant unknown beasts. The myth of the Kraken continued to thrive in the 19th century, popularized in literature and art. Alfred, Lord Tennyson, famously wrote a poem titled The Kraken, which described the beast slumbering in the ocean's depths, waiting to rise in a cataclysmic event. Herman Melville, in his classic Moby Dick also alluded to the Kraken, invoking the creature to illustrate the vast and fearsome mysteries of the sea. Such literary references perpetuated the legend, reinforcing the notion that the ocean held secrets beyond human comprehension. As stories of the Kraken circulated, sailors began to report sightings of large tentacled creatures. These accounts ranged from vague descriptions of massive shadows in the water to detailed claims of enormous arms breaking the surface and wrapping around ships. The most credible of these reports often came from experienced seafarers who had spent their lives on the ocean, lending a measure of authenticity to the tales. Over time, it became clear that these sailors were likely encountering giant squids, elusive creatures that inhabit the deep ocean. However, the mystery and fear surrounding these sightings gave rise to a widespread belief in the Kraken's existence. One of the most compelling accounts came from the French malacologist Pierre Denis de Montfort in the early 19th century. In his book Histoire naturelle, générale et particulière des mollusques *, Montfort described the colossal Kraken in vivid detail, asserting that these creatures were responsible for multiple shipwrecks. He went so far as to claim that the disappearance of 10 British warships in 1782 was due to the Kraken, pointing to illustrations of giant tentacles wrapping around ships as evidence. Although Montfort's theories were met with skepticism, they contributed to the growing body of myth and speculation surrounding the creature. In hindsight, it's easy to see why the legend of the Kraken endured for so long. The ocean, vast and largely unexplored for much of human history, has always been a source of both wonder and dread. The idea of a colossal sea creature lurking in the deep, capable of pulling ships under with ease, played into deep-seated fears about the perils of the sea. Moreover, Actual encounters with giant squids and other large marine animals likely fed the legend, giving rise to exaggerated tales of monstrous proportions. These creatures, which we now know as giant squids, can reach lengths of up to 40 feet or more, making them among the largest invertebrates on the planet. Yet, the Kraken legend was not purely a product of sailors' imaginations. The vast, dark and unknown depths of the ocean served as a fertile ground for such myths. When massive squids occasionally washed up on shore or were hauled up by fishermen, they provided a physical basis for the stories. These creatures, with their large eyes, lengthy tentacles and sharp beaks, were strange and otherworldly enough to spark fear and fascination. It's no wonder that early sailors, seeing a giant squid for the first time, might have thought they had encountered the infamous Kraken. While the existence of the Kraken was eventually debunked, the creature's legend persists. It lives on in literature, art, and popular culture as a symbol of the ocean's power and mystery. Today, giant squids continue to capture the imagination, and modern scientists have only recently begun to study them in their natural habitat. The elusive nature of these creatures and their deep-sea dwelling habits mean that even with advanced technology, there is still much to learn about them. The Kraken may not be real, but the inspiration behind the legend, giant squids and other mysterious cephalopods, remains a captivating reminder of the ocean's untold wonders. Long before humans began spinning tales of the Kraken, the ocean was ruled by real-life giants. These were the massive cephalopods of prehistory, whose fossils tell the story of an ancient and fearsome lineage. Cephalopods are among the oldest groups of animals still in existence today, having first appeared in the Cambrian period over 500 million years ago. This makes them older than sharks, reptiles, mammals, and even insects. Over the course of their evolution, cephalopods diversified into a wide array of shapes and sizes, with some reaching colossal proportions. One of the earliest and most notable families of giant cephalopods was the Endocerida, a group of large-bodied nautiloids that dominated the oceans during the Ordovician period. These ancient creatures had long, straight, conical shells that could grow up to 30 feet in length, making them the largest animals of their time. Unlike modern cephalopods, which are mostly soft-bodied, endocerids had heavy, rigid shells composed of calcium carbonate. This provided them with both protection and buoyancy, allowing them to navigate the shallow, warm waters where they thrived. The endocerids included several genera, but two of the most significant were Endoceras asterisk and Cameroceras asterisk. These two genera were so similar in appearance that paleontologists have often had difficulty distinguishing between their fossils. Both had long, cone-shaped shells and powerful tentacles, which they likely used to capture and subdue prey. However, subtle differences in shell texture have led scientists to classify them as separate genera. Despite these differences, both Endoceras and Cameroceras were apex predators, ruling the shallow equatorial seas that existed during the Ordovician. The evolutionary success of the endocerids was due in large part to their unique anatomy. Unlike modern squids and octopuses, which lack external shells, these ancient cephalopods had fully developed shells that housed most of their bodies. The shells served not only as protection, but also as a means of controlling buoyancy. By adjusting the gas and fluid levels within their shells, endocerids could rise or sink in the water column, allowing them to ambush prey from below. Their tentacles, armed with strong muscles and possibly equipped with primitive suction cups, enabled them to grasp and manipulate their victims. One of the key factors that contributed to the endocerids' dominance was their ability to grow to enormous sizes. Fossil evidence suggests that some species, such as Endoceras giganteum may have reached lengths of up to 30 feet, with their shells alone accounting for much of this length. If the soft tissues that extended beyond the shell are taken into account, these creatures could have been even larger. This made them formidable predators, capable of taking on a wide range of prey, from trilobites and fish to smaller cephalopods. It is believed that fully grown endosauриds were ambush hunters, lying in wait on the seafloor until unsuspecting prey ventured too close. Then, with a sudden strike of their powerful arms, they would seize their prey and drag it into their sharp beaks. Despite their size and predatory prowess, the endosaurids were not the only giants of their time. During the Cambrian and Ordovician periods, the oceans were home to a diverse array of large marine animals, including sea scorpions and strange arthropods like Anomalocaris. However, these creatures were no match for the endosaurids, which reigned supreme as the largest and most powerful predators. The only other animals that came close in size were certain species of sea scorpions, but even these were likely preyed upon by the largest endosaurids. The dominance of the endosaurids came to an abrupt end around 455 million years ago during the late Ordovician mass extinction. This event, one of the Big Five mass extinctions in Earth's history, was likely triggered by intense glaciation, which caused sea levels to drop dramatically. As the shallow equatorial seas receded, the habitats of the endosaurids were significantly altered, leading to their decline. In the aftermath of the extinction event, cephalopod diversity plummeted, and the once dominant endosaurids disappeared entirely. Although the endosaurids were gone, their legacy lived on in the cephalopods that followed. Over the next 200 million years, cephalopods adapted to new environments and gradually regained their diversity. During this period, new groups emerged, including the ancestors of modern squids, octopuses, and cuttlefish. These ancient cephalopods continued to evolve and diversify, developing new features such as ink sacs for defense and more sophisticated tentacle structures. While they never again reached the size of the giant endosaurids, these new cephalopods played an important role in the changing marine ecosystems of the Paleozoic era. Today, the endosaurids are remembered as some of the first true giants of the ocean, a lineage of ancient predators that once ruled the seas with their immense size and fearsome capabilities. Their story is a testament to the incredible diversity and adaptability of cephalopods, a group of animals that has survived for over 500 million years and continues to thrive in the world's oceans. Though their reign ended long ago, the legacy of these prehistoric Krakens lives on in the fossils they left behind and the modern cephalopods that still captivate our imaginations. The rise and fall of cephalopod giants is a story of resilience, adaptation, and the harsh reality of nature's cycles. In the ancient oceans of the Ordovician period, cephalopods like the endosaurids reigned supreme as the dominant predators. However, their dominance came to an abrupt end during the late Ordovician mass extinction around 455 million years ago. This event, often considered one of the most severe in Earth's history, wiped out nearly 85% of all marine species. It marked a major turning point for cephalopods, drastically reducing their size and diversity. The endosaurid family, which had grown to massive sizes and ruled the seas for millions of years, disappeared entirely, along with many other large marine predators. What followed was a long and challenging period for cephalopods as they struggled to recover and adapt to new ecological realities. The late Ordovician mass extinction was likely caused by a combination of intense glaciation and drastic changes in sea levels. As ice sheets expanded, sea levels dropped significantly, shrinking the shallow equatorial seas that had been the primary habitat of the giant endosaurids. These environmental changes disrupted the delicate balance of marine ecosystems, leading to the collapse of many species that had thrived in the warm, shallow waters. The cooling climate and shifting ocean chemistry dealt a particularly harsh blow to large, slow-moving animals like the endosaurids, which relied on stable environments and abundant prey. In the wake of this mass extinction, the survivors faced an entirely new world. The once expansive shallow seas had given way to colder, deeper waters, and many of the large predators that had previously dominated were now gone. For the cephalopods, this marked the beginning of a long period of decreased sizes and diversification. During this time, which spanned the Silurian, Devonian, Carboniferous and Permian periods, cephalopods were forced to adapt to new conditions and new competitors. As the top predators of the Ordovician disappeared, other marine animals, such as early fish and sharks, began to fill the vacant ecological niches. The reduced size of cephalopods during this period can be attributed to several factors. The colder, more unpredictable climate meant that large, slow-moving predators like the endossaurids were at a disadvantage. In their place, smaller and more agile cephalopods emerged, better suited to surviving in the rapidly changing environment. One group that thrived during this time was the orthosaurids, a family of straight-shelled nautiloids that managed to survive the mass extinction and gradually diversified into new species. Although not as large as their endosaurid predecessors, some orthosaurids still reached impressive sizes, with shells measuring several feet in length. Their adaptability and resilience allowed them to continue evolving and exploring new ecological niches in the altered oceans. The Devonian period, often called the Age of Fishes, saw the rise of new marine predators that further challenged the dominance of cephalopods. During this time, jawed fishes and early sharks began to diversify rapidly, developing new forms and hunting strategies. These new predators posed a significant threat to cephalopods, which were no longer the undisputed masters of the seas. In response, cephalopods began to evolve new features and strategies to cope with the changing dynamics of their environment. Some species, like the ammonites, developed coiled shells, which provided better protection against the growing threat of fish predators. Ammonites, a group of coiled-shelled cephalopods, first appeared in the Devonian and quickly diversified into a wide range of shapes and sizes. These creatures became one of the most successful groups of cephalopods, thriving in a variety of marine habitats. Ammonites had several advantages over their straight-shelled relatives, including a more compact and durable shell that made them less vulnerable to predation. Additionally, their coiled shells allowed them to regulate buoyancy more effectively, giving them greater control over their movements in the water column. As cephalopods adapted to their changing environment, they developed new anatomical features that helped them survive. One of the most significant innovations was the evolution of ink sacs, which first appeared during the Carboniferous period. Ink sacs allowed cephalopods to release a cloud of dark, viscous fluid when threatened, creating a smokescreen that confused predators and provided an opportunity to escape. This defensive mechanism, which is still used by modern squids and octopuses, became a key survival strategy for ancient cephalopods in a world where predation was becoming more intense. The Carboniferous period also saw the emergence of a new group of cephalopods known as pseudothocharids. These creatures, which resembled their orthosaurid ancestors, had long, straight shells and inhabited shallow, warm waters near the equator. Some species of pseudothocharids reached lengths of up to 8 feet, making them among the largest cephalopods of their time. Although they were not the apex predators that their endosaurid predecessors had been, pseudothocharids were still significant players in the marine ecosystems of the Carboniferous. Despite these adaptations, cephalopods remained relatively small and specialized during this long period of reduced sizes. They were no longer the dominant predators of the oceans, and their role in the food chain had shifted. Instead of preying on large animals, many cephalopods became opportunistic hunters, feeding on smaller prey like fish, crustaceans, and other invertebrates. This shift in diet allowed them to coexist with the growing populations of jawed fishes and early sharks, which had become the new rulers of the marine world. The Permian period, which followed the Carboniferous, brought with it further challenges for cephalopods. During this time, the Earth's climate underwent significant fluctuations, with periods of extreme warming and cooling. These environmental changes put additional pressure on marine life, leading to further extinctions and shifts in marine ecosystems. By the end of the Permian, cephalopods faced yet another mass extinction event, the Permian-Triassic extinction, which wiped out nearly 90% of all marine species. This event, also known as the Great Dying, was the most devastating extinction in Earth's history, and it nearly brought an end to the cephalopods altogether. However, despite the loss of many species, a few resilient cephalopods managed to survive the Permian-Triassic extinction. Among them were the ancestors of modern squids and octopuses, as well as the ammonites, which once again emerged as a dominant group in the newly reset marine ecosystems of the Triassic period. The recovery of cephalopods after the Permian-Triassic extinction marked the beginning of a new era in their evolution. With their competitors severely diminished, the surviving cephalopods had the opportunity to reclaim some of their former prominence in the world's oceans. During the Triassic period, cephalopods began to increase in size once more, adapting to the new ecological niches left vacant by the mass extinction. Ammonites, in particular, underwent a rapid diversification, evolving into a wide range of forms and sizes. Some species developed large, heavily coiled shells that provided enhanced protection against predators, while others adopted more streamlined shapes that allowed for faster movement through the water. This period of evolutionary experimentation led to the emergence of new families of ammonites, each with its own unique adaptations. As cephalopods began to recover and diversify, they also faced new challenges in the form of marine reptiles, such as ichthyosaurs and plesiosaurs, which had become the dominant predators of the Triassic seas. These formidable reptiles posed a serious threat to cephalopods, forcing them to develop new strategies for avoiding predation. Some species of ammonites responded by developing thicker, more robust shells, while others evolved defensive adaptations like spines and ridges to deter attackers. Despite these new threats, the surviving cephalopods continued to thrive and diversify throughout the Triassic and into the Jurassic period. The ammonites, in particular, reached new heights of diversity and abundance, becoming one of the most iconic groups of cephalopods in Earth's history. Their distinctive coiled shells and intricate patterns have left a rich fossil record, providing paleontologists with valuable insights into the evolution of cephalopods over millions of years. The long period of reduced size and diversity that followed the late Ordovician mass extinction was a challenging chapter in the history of cephalopods. However, it also served as a crucible for the development of new adaptations and innovations that would shape the future of these remarkable creatures. From the evolution of ink sacs to the emergence of coiled shells and new hunting strategies, cephalopods demonstrated their resilience and adaptability in the face of changing environments and new competitors. By the end of this period, cephalopods had once again regained their place as major players in the marine world, setting the stage for their resurgence in the Mesozoic era. Although they never reached the same colossal sizes as the endocarids of the Ordovician, the cephalopods that emerged from this long and difficult chapter were more diverse and better adapted to the challenges of their environment. This period of recovery and adaptation laid the groundwork for the rise of even larger and more complex cephalopods in the millions of years to come. As the Mesozoic era dawned following the devastation of the Permian-Triassic mass extinction, life on Earth began to recover and diversify once again. This era, which encompasses the Triassic, Jurassic, and Cretaceous periods, marked a time of renewed growth and evolutionary innovation in the oceans. Among the many marine creatures that thrived during this era were the cephalopods, which had survived the cataclysmic events of the Permian and were poised to reclaim their prominence in the marine ecosystem. With the rise of new families of cephalopods, including ammonites and belemnites, the stage was set for a new era of cephalopod giants. One of the most remarkable aspects of the Mesozoic era was the resurgence of cephalopods in size and diversity. Ammonites, in particular, experienced a massive radiation, evolving into a wide variety of shapes and sizes. These cephalopods, characterized by their coiled, chambered shells, became some of the most abundant and ecologically significant marine animals of the Mesozoic. They were highly adaptable, occupying a range of habitats and evolving numerous forms to suit different ecological niches. Some species developed large, robust shells to protect themselves from predators, while others adopted streamlined shapes that facilitated rapid movement through the water. The ammonites of the Mesozoic era reached impressive sizes, with some species growing to over 5 feet in diameter. One family of ammonites, the Cladocerids, stood out due to their enormous shell diameters, with some reaching up to 1.7 meters, 5.6 feet. To put this into perspective, the largest modern nautilus species only have shells about 20 centimeters in diameter. The sheer size of these ammonites provided them with protection against predators, allowing them to dominate the shallow marine habitats of the Triassic and Jurassic periods. Fossil evidence suggests that the largest ammonites were relatively well-armored, with thick shells and sturdy ribbing that made them difficult for predators to penetrate. However, despite their large size, these ammonites were not necessarily fearsome predators. Based on their anatomy, paleontologists believed that the giant Cladocerids were slow-moving filter feeders, preying primarily on small marine organisms such as plankton, crustaceans, and tiny fish. Their massive shells likely provided protection against the larger predators of the time, such as the ichthyosaurs and plesiosaurs, which roamed the oceans in search of prey. Although these ammonites were not apex predators, their size and abundance made them a key component of Mesozoic marine ecosystems. Another group of cephalopods that rose to prominence during the Mesozoic were the belemnites. These creatures were similar in appearance to modern squids, but had an internal skeleton made of a hard, bullet-shaped structure called a rostrum. This rostrum provided support for the belemnites' soft body and helped them maintain buoyancy. Belemnites were agile, streamlined hunters that thrived in both shallow and deep waters, where they preyed on small fish, crustaceans, and other marine animals. Some species of belemnites reached lengths of up to 10 feet, making them among the largest cephalopods of their time. One of the largest and most impressive belemnites of the Jurassic period was Megateuthis*, which could grow up to 3 meters, 10 feet, in length. This giant cephalopod had long, slender arms covered in sharp hooks that it used to grasp and subdue its prey. Like modern squids, Megateuthis* had a powerful beak that it used to tear apart its victims. Although it lacked the tentacles of modern squids, its arms were highly effective at holding onto slippery prey, making Megateuth this asterisk a formidable hunter in the ancient oceans. During the later stages of the Mesozoic era, the oceans became home to some of the largest and most complex cephalopods ever to have existed. By the time of the Cretaceous period, cephalopods were thriving in a variety of forms, from the coiled ammonites to the sleek, streamlined belemnites. One of the most notable developments during this time was the emergence of the largest ammonites in history. The genus Parapezosia*, which appeared during the late Cretaceous, holds the distinction of being the largest confirmed cephalopod of all time. Parapezosia* was a massive ammonite with a shell diameter that could reach up to 3.5 meters, 11 feet. To put this into context, the largest giant squids today reach lengths of about 13 meters, 43 feet, when their long feeding tentacles are included. However, in the case of Parapezosia*, the diameter of its coiled shell alone was nearly as large as the length of a giant squid, making it one of the most colossal cephalopods ever discovered. Based on fossil evidence, paleontologists estimate that Parapezosia* may have reached a total length of 18 meters, 60 feet, when fully uncurled, with its shell accounting for nearly half of this length. The sheer size and weight of Parapezosia* made it one of the heaviest invertebrates to have ever lived, with an estimated mass of around 1.5 tons. Its heavy shell was composed of thick, sturdy layers of calcium carbonate, providing protection against predators and enabling the ammonite to survive in deep, open waters. Although it is unclear what *Parapazosia* fed on, some paleontologists believe that it may have been an opportunistic predator, preying on a variety of marine organisms, including fish, crustaceans, and even smaller cephalopods. Others have suggested that it may have been more of a gentle giant, feeding on plankton and other small organisms in the water column. While *Parapazosia* was the largest ammonite of its time, it was not the only giant cephalopod in the late Cretaceous oceans. The Western Interior Seaway, a vast inland sea that stretched across North America, was home to several large cephalopods that coexisted alongside *Parapazosia*. Among these were *Tusoteuthis* and *Inoceramus*, which were members of a group known as the ankylosquid. Unlike the ammonites, these cephalopods lacked external shells and more closely resembled modern squids and octopuses. However, recent research suggests that *Tusoteuthis* and its relatives were not true squids, but rather a distinct group more closely related to octopuses. Both *Tusoteuthis* and *Inoceramus* were large, plump-bodied cephalopods with mantles that resembled those of modern cuttlefish. These creatures could reach lengths of up to 3 meters, 10 feet, and had fins or wings attached to the sides of their mantles, which provided stability and increased speed in the water. Their size and streamlined bodies indicate that they were active hunters, pursuing a wide range of prey, including fish, marine reptiles, and other cephalopods. Despite their resemblance to squids, these giant cephalopods had a more robust body structure, making them significantly heavier and more imposing. The Western Interior Seaway was not the only region to harbour giant cephalopods during the Cretaceous period. Fossil evidence from Japan has revealed the presence of several massive cephalopods, including giant squids with beaks larger than those of any living species. Paleontologists have identified 2 genera, *Haberoteuthis* and *Yoeotethis*, based on the size and structure of these fossilized beaks. Although the exact size of these ancient squids is difficult to determine from the beaks alone, researchers believe that they were among the largest marine predators of their time, capable of preying on a wide variety of animals in the waters around Japan. One of the most intriguing discoveries from Japan is a fossilized beak that is significantly larger than those of *Haberoteuth, this asterisk and *Yoeotethis*, suggesting the existence of an even larger cephalopod. However, paleontologists have not yet been able to assign this beak to a specific genus, and no complete fossil remains of this giant squid have been found. This mystery has led to speculation that Japan's ancient waters may have harbored a yet unknown species of giant cephalopod, one that rivaled or even surpassed the size of the colossal squids found in today's oceans. The existence of these giant cephalopods in different parts of the world during the Cretaceous period highlights the incredible diversity and adaptability of these ancient creatures. Despite the mass extinction events that had previously decimated their populations, cephalopods continued to evolve and thrive in new and innovative ways. From the colossal ammonites of the Western Interior Seaway to the mysterious giant squids of Japan, the Cretaceous oceans were a haven for cephalopods of all shapes and sizes. Among the many legends that have emerged about ancient sea creatures, few are as intriguing or as controversial as the legend of the Triassic Kraken. This hypothesis, proposed by paleontologist Mark McMenamin, suggests that a massive cephalopod once roamed the oceans during the Triassic period, 215 million years ago. The idea of a Triassic kraken arose from the discovery of a peculiar arrangement of ichthyosaur bones, which McMenamin interpreted as evidence of a giant cephalopod preying on these marine reptiles. According to McMenamin's hypothesis, the Triassic kraken was responsible for the deaths of 9 giant ichthyosaurs, which were found buried together in what appeared to be an organized pattern. He suggested that the arrangement of the bones resembled a carefully constructed graveyard created by the Kraken after it had killed and consumed the ichthyosaurs. Based on the size of the ichthyosaurs, McMenamin estimated that the Kraken would have needed to be at least 30 meters, 100 feet long to successfully hunt such large prey. If true, the Triassic Kraken would be the largest cephalopod ever discovered, surpassing even the largest modern squids and ammonites. However, McMenamin's hypothesis has been met with widespread skepticism among paleontologists, primarily because there is no direct fossil evidence of a cephalopod of this size from the Triassic period. Additionally, the idea that a cephalopod could kill and organize the remains of multiple ichthyosaurs is highly speculative, given the limitations of cephalopod behavior and anatomy. Critics of the Triassic Kraken hypothesis point out that there are many other possible explanations for the arrangement of the ichthyosaur bones. For example, the ichthyosaurs may have died as a result of a beaching event or a sudden environmental change, such as a drop in oxygen levels. Over time, currents and natural processes could have moved the bones into their current positions, creating the appearance of a deliberate pattern. Furthermore, the idea of a cephalopod large enough to kill and arrange 9 giant ichthyosaurs strains the limits of biological plausibility. Despite the lack of definitive evidence, McMenamin's theory has captured the public imagination, fueling speculation about the existence of giant undiscovered cephalopods in Earth's ancient oceans. In 2011, McMenamin reignited interest in the Triassic Kraken when he discovered a fossilized beak in the same area where the ichthyosaur bones were found. Although the beak was much smaller than he had hoped, measuring only 5 centimeters in length, McMenamin argued that it belonged to a large bus-sized cephalopod that could have preyed on the ichthyosaurs. This new discovery did little to convince skeptics, as the size of the beak was comparable to those of modern giant squids, which are not capable of hunting large marine reptiles. However, the possibility of a large cephalopod existing during the Triassic period raises intriguing questions about the evolution and diversity of cephalopods. If nothing else, the Triassic Kraken hypothesis highlights the gaps in our understanding of ancient marine ecosystems and the potential for undiscovered creatures lurking in the fossil record. As fascinating as the legend of the Triassic Kraken may be, it remains highly speculative and unsupported by direct evidence. Nevertheless, it serves as a reminder that the ancient oceans were home to a wide variety of cephalopods, some of which reached sizes that rivaled the largest marine animals of today. Whether or not the Triassic Kraken ever existed, the possibility of other undiscovered cephalopods lurking in the depths of Earth's history continues to captivate the imagination of scientists and enthusiasts alike. The story of cephalopod evolution is one of adaptation, survival, and occasional dominance. From the early giants of the Ordovician to the resilient survivors of the Mesozoic, cephalopods have repeatedly adapted to the challenges of their environment, evolving new forms and strategies to survive in a changing world. Although the Kraken may be a myth, the real-life cephalopods of Earth's past were every bit as extraordinary as the legends they inspired. The fossil record continues to reveal new insights into the ancient giants that once ruled the oceans, offering glimpses into a world where colossal creatures roamed the seas and fearsome predators lurked in the deep.